So do that. It's going to be due on Thursday to my mailbox. Thank you for starting the recording. Whoever did that, A+ to you for the day. Redeemable for probably nothing, but a hearty thumbs up. Good job. Okay. So that's really the only announcement. Today we're going to finish the matrix and reinforcement materials notes, and then on tomorrow, aka tomorrow, we'll start in on manufacturing of composites. All right. So let me pull in the matrix and reinforcement notes, and we'll sort of be on our way. All right. Get rid of this flaming. This is fine. And we'll remind ourselves to kind of go through a brief recap of what we talked about last time. Yes, sir, we have a question. The question is, when are the lecture slides going to be put up for tomorrow's class? And the answer to that is probably right after this lecture. Okay. So they're done. I just got to put them up there. Okay. So remember we were talking about matrix and reinforcement materials. And remember a composite is made up of 3 constituents. Though the topic of this particular lecture is matrix and reinforcements, I will talk a little bit about the interface, which is the 3rd component at the end. So we had a kind of a classification, and first we sort of started talking about generally these matrix and reinforcements and their general purposes. The reinforcement, we're going to talk about continuous reinforcement mostly in this class. We'll also talk some about short fibers and particulates. But what we talked about mostly in last lecture was matrix materials. And we're separating and kind of classifying matrix materials by the temperatures which these different matrix materials can really withstand. And polymer matrix composites being usually the most common that you'll see, with service temperatures maximum of up to 200, though it can be plus or minus depending on the particular polymer. Metal matrices, depending on the matrix, can go up to about 800 C, and ceramic matrices up to about 1800. Interestingly, I did bring a metal matrix composite today to class. It's kind of in this bag right here, maybe a little hard to see. I'm going to pass this around, but you can sort of see this metal matrix composite. This is sort of a semi-cylindrical piece that was part of a wheel housing. And it's a graphite and aluminum matrix composite. So pretty cool. Maybe we can sort of pass that around, and I'll show it kind of at the end of class, but you can get an idea for how heavy these metal matrix composites are. And then ceramic matrices up to about 1800 C. All right, so we kind of went over the different matrices in gory detail. Polymer matrices, thermoset, thermoplastic, the differences, the drawbacks, the benefits, so on and so forth. Same things for metals and same things for ceramics. So just kind of reminding you what we did last time, talking about polymer, metal, and ceramic matrix materials as the backbone of your composite. And a couple things I'll remind you: polymer, pretty much the best, very lightweight, a lot of different polymers to choose from, good chemical resistance. But if you need higher temperatures, metal or ceramics are the way to go. And generally we don't use metals and ceramics because metals, you're losing the benefit of composites in the first place because metals are generally heavy. And ceramics, we would use more often, except they're very brittle, so not very good for applications where you might have fracture toughness requirements. All right, so let us continue moving forward now to reinforcement materials. So moving in on new material, no pun intended, except kind of pun intended. All right, so reinforcements. Reinforcements are more generally classified not by the temperatures which they can withstand, like the matrix materials are, but instead by the dimensionality of the reinforcement. All right, so in this class, we're generally going to talk about continuous fibers for the most part. All right, continuous fibers are long and continuous, as the name implies, and they have an aspect ratio L over D of usually 1,000 or more. So this is what you would normally think of when you kind of think of a carbon fiber or glass fiber reinforced epoxy material. Very large aspect ratios, the diameter, usually carbon fiber, glass fiber in the 5 to 10 micron range. And so if you have, a meter long piece, you're talking about huge aspect ratio there. All right. They can be incorporated in a variety of different patterns. You can be unidirectional, meaning all sort of in one general direction. Or it could be woven, meaning you have sort of like an over-under pattern. That's a lot like how your shirt works, right? So you have sort of like this over-under woven structure. It could be braided, and so on. We'll talk about a little bit more about architectures a little bit later. We'll also talk about short fibers in this class, aspect ratio of somewhere between 3 and 500. It's generally considered short fiber. and then particulates are nearly spherical. The mechanics associated with short fiber and particulate reinforcements are markedly different from the mechanics of continuous fibers, and when we get to the models of the mechanics for each one of these three different types, we'll dive in on the general differences between all of these um, different types. Okay, so let's dive in and look at a few more of the properties in specific and how the reinforcement might compare to the matrix. All right. The reinforcement phase chemistry is built to give you that strength and stiffness, which is sort of the job of the reinforcement. All right, so it's usually consisting of elements from the first three rows of the periodic table because they're reactive and generally strong and stiff and light. Okay, so these early elemental materials are generally characterized by things like covalent bonding and high strength, high stiffness, low density, low toughness. Okay, so these are all things that we would want for our reinforcement phase, aside from maybe low toughness. These are all generally good things. Some common materials that you might see for reinforcement and composite materials are amorphous glasses. So when you hear like a glass fiber reinforced plastic, typically like an amorphous glass material. Carbon, obviously, carbon fiber composites. Polymers, natural fibers like wood fibers, and ceramic fibers are also common as well. So when you're using a ceramic matrix, you usually need a ceramic fiber, right? Okay, so those are very common materials. All right, so here is an example of some general comparison using a stress strain curve of how these fibrous materials would look if you loaded them in tension. All right, so we have kind of like a stress strain diagram here with a variety of different materials showing. On the bottom here is generally an epoxy matrix. All right, so this epoxy matrix is low stiffness. You see it has sort of the lowest slope on this stress strain curve compared to all the others. And it gives you a general idea of the stiffness and strength of a matrix phase, which is a typical epoxy phase of a composite, versus the stiffness and strength of what would be your reinforcement phases. So all of these sort of lines on this particular graph are stress strain curves of reinforcement phases that you might see. So here we have a sort of a glass material, a glass reinforcement, glass fiber. This here is a different type of glass, resonant pregnated strands, graphite or composite strands, boron fibers. So this is a ceramic fiber being very, very stiff, and high molecular graphite yarn also being very, very stiff. So you can see like they're just pulled here in this general example to failure, and you see about where the strengths of each one of these lie, right? The Y value here indicating the strength, and then the slopes of these would indicate the stiffnesses. So just want to give a general sense of how stiff and strong the reinforcement phase is, typically in comparison to the epoxy phase, the matrix phase. All right. This is more of your Ashby style plot that looks at the specific properties, meaning that the properties that have been normalized by mass. So we have specific strength on the Y and specific modulus or stiffness on the X. And this is, again, the further up and to the right you can go, generally the better material that you can make in terms of specific properties, right? Strength and stiffness to weight ratios, right? So here are some good examples here. And on this particular gamut are all the different types of reinforcement I've kind of talked about. Kevlar being a polymeric reinforcement, a polymer fiber. S-glass, E-glass, these are ceramic type fibers. A glass is a ceramic. And just for comparison, you see where steel falls relative to these other reinforcement phases. All right. Okay. Now, reinforcements are nice, but remember the drawback of just reinforcements alone is that they cannot hold compression, right? So if you just take a single glass fiber and you pull on it, yeah, it's great. But if you compress a single glass fiber, it's just going to immediately buckle and you get nothing out of it. All right, so you need help of the matrix to sort of bond all these things together. Now let's talk a little bit more specifics about some of the most important reinforcement materials that you'll see in the world, specifically glass and carbon fiber. Now, glass fibers are amorphous, these amorphic ceramics, okay? Glass is by far the most common reinforcement for fiber reinforced composite materials. It's generally cheap, it's generally low density, and it has a high temperature and chemical resistance. Makes it a really good choice for reinforcement phase. All right? It's amorphous, meaning it has sort of no crystalline structure inside of it. and it kind of ebbs and flows between its melt and its solid state. All right, so an amorphous material doesn't really have a true melting point. It's just a very, very viscous liquid, very viscous. All right, so the chemical structure of glass is this silicon dioxide, SiO2, and then different glasses can be created by sprinkling in different ions. So think about your metal alloys. All right, there's analogies here, right? So if you want an aluminum 6061 alloy, maybe you sprinkle in a little bit more magnesium, maybe you have a little bit more potassium, and that's kind of how you get a different type of aluminum alloy. Same idea here for glass fibers. We have different alloys or different types of glass that can be used in different situations depending on what the application calls for. And the ions that are sort of included and floating around this amorphous silicon dioxide structure will give you the changes or the different properties of the glasses that you might want. Okay, so some additional ions that you might see, typically salts, will be sodium ions, potassium ions, etc. Okay, it's going to change the stiffness and the strength. It'll change electrical conductivity, and it'll change chemical stability. Right. So the four most common, I'd say this probably constitutes, I don't know, 99% of glass fibers in application, are E-glass, C-glass, A-glass, and S-glass. They just all have a singular letter defining the type of glass that might be used as the reinforcement. I've kind of got a chart there that details a lot of the chemical differences between the two. I include that there just for reference. You don't need to memorize the numbers in that table. It's just informational. But you do or should be aware of the different suffixes associated with these glasses. All right, E-glass is by far the most common material used for glass reinforcement. Um, it's the cheapest. You have good electrical conductivity, and generally E-glass has very good optical properties, meaning that if you use an epoxy matrix with E-glass fiber to make your composite, you're going to have very good index matching. I mean, you'll be able to see through that composite generally very well. Okay, it's a nice benefit of the E-glass material. C-glass is for chemical resistance, so it has ions included in it to give it the highest chemical resistance possible. Usually it can resist some pretty bad acids, right? So C-glass, I don't know about hydrofluoric acid, but some strong acids like hydrochloric it can withstand, right? All right. A-glass is alkali glass. It's soda glass, basically. It's very, very cheap. Good all around, but E-glass is slightly superior in terms of strength and stiffness. All right. And then S-glass. S-glass is probably the second most common glass fiber reinforcement used in composites, and S-glass has the highest strength and the stiffness of all of them. Okay, so that chart kind of outlines the differences in their moduli and the relative inclusions of the various ions to give them those sorts of properties. Right? Glass fiber manufacture is freaking awesome. Okay, I've been to a glass fiber manufacturing plant, and it's so sweet to see this in production. All right, so what happens is, you get this amorphous, heated up, like slurry of glass. Okay, it's in this big basin, like at the top of this factory floor, basically. All right, and you heat this up. You got all the silicon dioxide. You pour all your salts in to make the type of glass that you want, and then you feed that molten glass to these like spinners or these spinnerets or these like nozzles. And these nozzles are in an array of like thousands of openings. And the mass of the glass just pushes all of the molten glass through these openings to kind of make these own individual fibers and come out off of the line. So that picture that you see there on the right-hand side of the slide, that is like thousands of individual glass fibers coming through their own individual nozzles in sort of the molten state at the bottom and coming down to take up rills below that. So it's freaking sweet process. And it's going so quickly. Like they make meters and meters and meters of this like per second. Okay, so it's just incredibly fast. All right. So it's this really awesome process. Uh, when the fibers are actually coming through the nozzle and sort of exposed to the air, a sizing is applied to them. And I'll describe what a sizing is in just a second, but it's like a liquid application. Sizing in the composites world doesn't have anything to do with the actual dimensions of the fiber. So don't get confused when you hear the word size. A sizing is a liquid application on the surface of a fiber to give it more chemical bonding to the matrix of choice coming up. And I think that's on the next slide here. So a sizing is applied to the glass as it's sort of coming through these nozzles on the backside. So there's like the sprayer that's hitting all of these individual fibers as they're coming through their individual nozzles. And so this sizing doesn't have anything to do with the dimension of the fiber. It's actually a surface treatment that's applied to the glass as it's coming through the nozzle. All right. It's usually in an aqueous form, okay, so it's like water shooting at this glass, but the water has like a small amount of chemical reactants in it that will stick to the surface of the glass and allow it to be more chemically reactive with the matrix once the time comes to actually make the composite. So, the purpose of applying this spray, this sizing onto the glass before the composite manufacturing process is you got all these glass fibers like coming through this production, and if you didn't spray them with water, the amount of static in that environment would be insane. Okay, all the fibers would start like sticking to each other just because of static reasons, static electricity. And so, one thing that this water spray, this sizing application does, is it stops the fibers from sort of like sticking to each other as they're coming out of the nozzles. All right. The second thing that it does is it sort of reduces the friction as the glass fibers are being taken up on sort of the mandrels on the bottom of the production. All right. So it sort of serves a dual purpose. All right. That's just in the production for the fibers itself. Now, the sizing is also useful, and its main purpose is to give a chemical functionality to the surface of the glass so that when you go to actually make the composite, there's a chemically reactive surface on the fiber that will help you bond to the matrix, right? So it's helping you build an interface, the third component, right? Okay. So there's some information about the chemistry here, but basically the idea is that you're giving chemical functionality to the surface of the glass to help you bond to the matrix that you're going to be using later. All right, that's glass. Carbon is a whole other monster. All right. Carbon fibers are the strongest and stiffness reinforcement that you can have for making composites, and probably the sexiest. I mean, I'm not gonna lie, carbon fiber is, one of its main attractions is that it looks pretty awesome. So if you get in a car and you got like this carbon fiber paneling, you're like, ooh, that's nice. Like, I like that. That's cool. All right. So high strength and stiffness, but it's very expensive. So where glass is about $3 to $5 a pound, carbon fibers are about $100 a pound. So if you're going to use carbon fiber as your reinforcement, you need some justification for the, I don't know, 30 times price tag, okay, compared to glass. All right. You'll sometimes hear carbon fibers referred to as graphite fibers, but that's really an older terminology. So you'll hear carbon fiber almost exclusively now. Graphite is, the name that was previously used because that's kind of the backbone of what the structure is. It's a graphitic structure. All right. Now, production of these is actually something that's done in the U.S. And there's a really big plant that recently just opened up in South Carolina. This article is like a couple years old now, 2018, but still, carbon fibers are produced in the U.S., which is really kind of a cool thing. Most of the production was reserved for Japanese um, companies like Tijan, for instance, but here we have some now in the U.S. Specifically, this particular plant is driven by BMW's desire to establish a market in the United States, which is kind of cool. So you see a bunch of carbon fibers spooled up on mandrels on what's known as a creel, which is a series of individual um, sort of these woven individual strands on this whole array of carbon fibers there in that picture. They can be used then to create some pretty awesome stuff. Like I think this carbon fiber epoxy violin is a pretty cool example. Right? So very light violin. I bet if you held it in your hands, it'd feel like a couple ounces only. Be kind of cool. All right, so their chemical structure is very unique, and that's what makes carbon fibers so incredibly strong and stiff. Right? Is you probably talked about this in your material science class, but carbon fibers generally tend to arrange themselves in these basal planes, right, where they have generally like a flat planar structure, which is called the turbostratic structure, right, and it's layered on top of each other. Okay, so if you've ever looked at, for instance, the chemical backbone of graphite that's in your pencil, it would look very similar to this, where you have these carbon atoms sort of stacked on top of each other in this turbostratic sort of arrangement. Okay, so the way that carbon fibers leverage this is they take these planes of carbon and they fold themselves sort of back onto each other to create what you see on kind of the right-hand side there is that like folded carbon fiber structure, where all these planes are sort of like woven into each other and stacked on top of each other and formed into sort of like a, I don't know, this crazy sort of arrangement. But the idea here is that the covalent bonds that occupy the plane are along the length of the fiber. And those bonds are generally very, very strong. So if you can imagine taking what is kind of, I'm going to use my arrow here, this general structure with all these carbon rings, and thinking about loading that in any direction that is in this particular plane of this series of rings, that's more or less what you're doing when you're packing all of the carbon fiber turbostratic structure across the loading plane of the fiber. Okay? But because of that, carbon fibers are very anisotropic. They're very, very strong in the direction of the length of the fiber, but they're very weak across the fiber. So if you could somehow load the carbon fiber across the fiber, you're basically loading across the individual planes that make up that carbon fiber. And that's a very, very weak bond. It's a van der Waals bond, okay? So it's only really held by the attraction and repelling of the charge of the individual planes that make up the turbostratic structure. All right, so this is how carbon fibers have immense strength in the length of the fibers, but very, very weak across the fibers. All right. So here we go with some numbers: 300 GPa in the longitudinal direction and 15 GPa in the transverse direction. So there you go. Gives you an indication of the relative stiffnesses. All right. Processing of carbon fiber. Processing of carbon fiber is complicated, and for those of you that end up getting the carbon fiber manufacturing depth prompt for your depth manufacturing assignment, you're going to go into this in more detail. But the basic idea is you start with some carbon precursor. All right, so this is some carbon that got mined from the ground, or it's in some general basic form from the earth. And those general basic forms are polyacrylonitrile, pitch, and rayon. Those are the most common that are used in pre-production for carbon fibers. All right. So this general process, you begin with one of these particular precursors, and then you stabilize the carbon itself. Okay, so you heat it up to 300, 200, 300C in oxygen to provide sort of like an oxygenized carbon structure. Okay, then you go through the carbonization step where you basically like burn off all the non-carbon components, right? So carbon has a very high resistance to temperature generally, but a bunch of the BS that comes along with getting carbon from the earth is probably not going to survive 1000C all that well. All right. Then finally, you have a graphitization step, which you're pulling on the carbon to sort of align these planes in the direction that you want them to go, and then you take it up. Okay. So here's one of the original patents has sort of the production process for carbon fibers themselves. And this details kind of the various temperatures along the way. And there's kind of a lot of detail here. Probably you don't need to sort of memorize everything here, but it will be useful for you if you go into depth on carbon fiber manufacturing for your manufacturing depth assignment. Okay. So glass fibers, carbon fibers, check, check. Last one we're going to talk about as common reinforcement for composite materials is polymer fibers. And polymer fibers are usually high strength, usually high stiffness, but can give you an added benefit of toughness. So when you're talking about a glass fiber, for instance, glass is very brittle, all right? But polymers can be very tough. So if you for some reason need increased toughness, then polymer fibers are for you. So some polymer fibers you may have heard of in the past. Kevlar is probably the most common that you've heard of. Spectra and Vectra are also very commonly successful commercially. And they also offer some interesting thermal and chemical properties as well. Compared to carbon, they're relatively cheap, but compared to glass, they're still a little bit on the expensive side. All right. Polymer fiber is usually manufactured with sort of an extrusion process. So you get all your polymer melt and some extruder, and you force that polymer melt through a nozzle, and you can pull on that and draw that through to create your filament. That's usually how it's done. So here's an example of Kevlar fiber and its particular structure. And again, like I said, the benefit of these polymer fibers is they're very tough. And so they have a lot of ability to sort of expand, or that, carbon fibers and glass fibers don't. That's why Kevlar is commonly used in body armor. I shoot you, bang, bang, and you're wearing Kevlar, well, that polymer fiber, which is the backbone of that body armor that you're wearing, can absorb the energy associated with that bullet because you have very high toughness of these particular fibers. That's why Kevlar is commonly used as a backbone for the composite that is usually in your body armor. Okay? Not your body armor. Hopefully you're not wearing body armor, but body armor in general. Okay? God, I hope you guys are wearing body armor. Well, these days, maybe. I don't know. It's a little suspicious out there. But okay. Uh, I digress. Polymer. Why is it so strong? Well, it's very strong because usually polymers have very long chains. Okay, so polymeric chains, thermoplastic chains are generally very, very long and can accommodate a lot more stretching than like the amorphous glass structure, which is much more brittle. Okay, so here's an example of this sort of like layered structure of what would be a Kevlar fiber. And interestingly, the Kevlar fiber backbones, which would be like the chains of the polymer, have kind of a zigzag sort of pattern as it sort of moves down the length of the fiber. And this is just because of how the thermoplastic tends to bunch up chemically when you're in the production here. So it has this zigzag pattern, meaning that when you pull on it, it has the ability to sort of stretch a lot more than glass or carbon fiber would. Okay, so very, very tough. Excellent toughness. Excellent, I say. Excellent. Used in body armor. All right. Spectra, it's a little bit different, but ultra-high molecular weight polyethylene, which has been made into fiber. It is probably the most basic of polymers, just as very simple carbon and hydrogen chain. It's such a basic. It probably likes pumpkin spice lattes, all right? It's so basic, all right? Very anisotropic. I gotta do something here. I gotta, make some jokes. Pumpkin spice, I like pumpkin spice. Okay, I'm basic. What do you want me to say? All right, and then Vectran. This is another polymer fiber. It's polyester. And Vectran is very useful for its thermal stability. So it's actually used in space suits. Pumpkin spice season. Yes, it is. All right. So Vectran is actually used in spacesuits. So spacesuits very high thermal resistance and generally very light. So this is what you want, what you really, really want. So tell me what you. Okay. All right. So carbon fiber, glass fiber, and polymer fibers by far the most common for fiber reinforced polymers. But you may see other reinforcement types utilized in composites. Some ceramic fibers are common, though ceramic fibers are really only reserved for situations where you need very high thermal resistance, just like ceramic matrices are really only reserved for high thermal resistance. And the reason ceramic fibers mostly aren't used is they're brittle and they're super expensive to make, right? So if you want to make a ceramic fiber, you have to like basically grow them in a lab. Like ceramic fibers themselves aren't really naturally occurring things. It's not really easy to make a significant amount of short boron fibers. All right, this is not an easy process. All right, so not very common to see ceramic fibers ever. All right, so that's that. Natural fibers. This is something that is gaining more and more popularity these days. All right, because natural fibers are themselves good products in nature. Okay, trees use natural fibers. Like word alert. All right. Um, so fibers in the natural world tend to be useful for what they are, right? So they're in the natural world and they're very useful. Now the issue is that the natural fibers that might make up jute or hemp or basalt or whatever generally don't have any reason to bond to, let's say, epoxy. Okay, so the surface of a hemp fiber isn't characterized, it isn't chemically favored to bond to an epoxy for any real reason. Okay, it's chemically favored to bond with other living things like the lignin in the trees. Okay, so when you're thinking about using natural fibers, it's actually hard to make a nice interface between the natural fiber and your matrix material, whatever the matrix material might be. Also, dead natural fibers, which most of the time it's going to be dead if you're using it, don't really hold up well over time, right? So if you have like a hemp fiber and you have it sitting around for like 3 months, it's just not very. It's not going to be very good for your composite. All right, it's going to turn brittle. It doesn't have the vivacious nature that it does when it's in the plant itself, right? It doesn't have any way to continually revitalize itself to provide the strength that it once had in its living form. All right, so not great chemical compatibility, and generally the mechanical properties are not quite as good. All right? So here's a final summary of some of these reinforcements that we've talked about. We have, again, the specific stiffness and specific strength with a variety of materials. Would aramid be another type? Thank you for the question, David. Aramid is Kevlar. Kevlar is a type of aramid fiber. So that was the question in the chat. Is aramid another type of fiber? So Kevlar is an aramid fiber. All right. Aramid refers to the structure in the backbone of the polymer itself. Kevlar is the trade name. All right. So Kevlar, a couple of different varieties here. Low specific stiffness, but very high strength. Graphite, high stiffness, high strength. You can see all the graphite or the carbon fibers occupying kind of the upper right-hand side here. Then you get your ceramic fibers here, boron, S-glass, E-glass, and steel and aluminum, again, kind of occupying sort of the lower left of this chart, showing that their specific properties are not the best. All right, thermal stability. This could be important if you need to select what fiber you're going to use for your application. And let's say your application is the re-entry heat shield of a shuttle. Well, you probably don't want to be using Spectra, I'll tell you that. All right. So you'll need to keep these thermal stabilities in mind. Importantly, too, is the toughness. It's basically how much stretch you get in these individual fibers before they fail. Kevlar is the best, strain to failure of like 2 to 10%. What if you petrify the organic fibers before they turn dead? Says Kevin. They turn dead. I guess you know, if you encased a living fiber into an epoxy, yeah, but it might still embrittle inside of that petrification, as you say. All right, so toughness, Kevlar between 2 and 10%. So this is the highest strain to failure, the most stretch, the best toughness. And then the worst toughness, obviously, are these ceramic fibers. We always talk about ceramic very poor in impact applications and fracture mechanics. So there you go. Carbon and glass, also quite low relative to polymeric fibers, but generally better than ceramics. All right. Now, we've talked about these individual fibers, but most of the time, fibers don't exist in composites as individual strands. Usually they're woven into some architecture, like my clothing, for instance. You know, my clothing, this is like a woven cloth, okay, over under pattern of these individual fibers create what is my shirt, right? So after manufacture of these individual fibers, it's typically woven into some architecture. And these architectures and their names have very specific meanings in the world of fabrics and textiles, okay? So we need to go over those very specific definitions first. So some of the architectures include toes, so not T-O-E-S like what's on your foot, but T-O-W-S. So if you write a manufacturing document and you write T-O-E-S for your fibers, oh, I'm going to just throw it in the garbage, okay? T-O-W, it's a fiber toe, T-O-W like tow truck, all right? It's a collection of fibers in a single bundle, usually between 300 and 10,000 fibers. So when you see fibers coming off a creel or fibers in some arrangement, it's usually in a toe structure. So I'll see if I can find an example here of a fiber toe. All right, I'm going to pluck one off of a woven carbon fiber here. This here is an individual carbon fiber toe. You sort of see that there. This strand, it kind of looks like, I don't know, a large hair, I guess. But if I were to like turn it on its side and zoom way in on the camera, you would see tens of thousands of individual little carbon fibers, okay? So I'll get this out here. I'll pass this around. And you can actually, maybe if you want to like pull some individual strands out, you can take a look. And you can just throw that in the trash when you're done. I've got plenty. But that is an individual carbon fiber toe, and that individual toe contains about, I think that's a 6K, meaning it's got 6,000 fibers in that one particular toe, right? So crazy, cray. All right, that toe you noticed is very straight, okay? It's not sort of intertwined or interwoven, all right? All the strands are sort of in line with each other, okay? And so that individual toe has these very flat architecture. That's different from a yarn, where yarns are just woven into each other and sort of it's not all straight together, okay? You have a question? Not much except their own static. Yeah, so the question is, what is keeping those fibers together in that individual toe? And the answer is basically just static, okay? There's no adhesive keeping those individual toes together. When they get woven into like a plane weave structure, for instance, that actual structure itself would also be holding them together. Okay. All right. So yarns are very similar to tows, except that they're like woven or kind of like bundled into each other. All right. With twist. Rovings. All right. Rovings are bundles of fiber strands that are kind of woven on a cylinder without twist. I'll show a picture of this in just a second, but imagine that fiber tow that was wound onto a drum. We would call that entire winding a roving. Right? Woven rovings are just what they sound like. A roving, that's that individual bundle of tows on a particular creel that has been woven in some pattern, right? A plain weave, a twill weave, a satin weave, so on and so forth. Right? Unidirectional materials, these are fabric architectures where all of the fibers are moving in one general direction. So I want to see if I have an example. Yes, here's an example of a unidirectional carbon fiber fabric. Maybe we can see this, maybe we can't, but all of the fibers are sort of running up and down in this particular mat. There's no woven behavior to this. They're all sort of moving up and down. That would differ from something like this. So where we see here, there's kind of these individual toes like woven over and under on the top of each other. This here, what you see in the image, is a woven roving, right? So that's kind of what I described a little bit above. And this here would be a unidirectional fabric where all of the fibers are sort of moving in a singular direction. So I'll pass these around as well. These I will need back. All right. You can have individual mats. So mats are basically like chopped fibers that are just sort of, splayed out onto an individual mat. And these mats can be of woven or sort of continuous or non-continuous. That's a pretty thin mat. Let's get something a little better here. Getting out my goodies, guys. Getting out my goodies. All right, here's another example of a toe. You can sort of see here that's been a little bit separated. Okay, but here is a sort of a woven or a chopped mat. So this is a strand mat. It's very thin. So you see this like veil structure here. It's very thin mat, and there's no directionality to the fibers. They're sort of in a random orientation. Okay, so this is a very thin mat, useful for kind of providing like surface finishings to, let's say, the hull of a boat. That would be a good example. All right, so careful with this one. I'll pass this around as well. That's a mat, continuous strand mat. And then you could have chopped or milled fibers as well, which is just basically putting a bunch of these fibers into a ball mill, chopping them up, and giving yourself some short fibers. All right, so here are some pictures of those things I was just describing. See the chopped strand mat? That's similar to what I'm passing around sort of in class now. You can have chopped strand or continuous strand. Chopped meaning that they have a slightly lower aspect ratio than what you would see in the continuous strand mat. The woven roving, or the roving there with a single fiber toe. This is what sort of a roving looks like. So it's this single fiber toe that's been wound and wound and wound and wound and wound and wound and wound on this particular mandrel. Okay, so this here would be referred to as a roving. And then if you took this singular strand and arranged it into a pattern with multiple toes in one singular direction, here this kind of moving left to right, this is a unidirectional particular pattern. You have chopped fibers, and you can also have yarns. Yarns are, again, very similar to toes, except they have twist. You can take the roving and weave it into a woven roving weave. Say that 10 times fast. I dare you. I dare you. Woven roving weave. Woven roving weave. It's just like impossible, okay? I'm tired. I'm old, all right? Some examples of woven roving weaves, or what some people might generally refer to as woven materials, for simplicity's sake. The three most common and the three that you should be aware of and might get tested on in the future would be, thank you for that, plain weave, which is just this basic over, under kind of weave that is, what most of your shirts are probably made of. It's very simplistic. You have a twill weave, in which you could have something that goes like 2 toes over, 2 toe, 1 toe under, 2 toes over, 2 toes under, so on and so forth. Okay, so here's an example of your twill weave. So maybe you can sort of see over 2, under 2, over 2, under 2, sort of repeating itself. Right, so here's your twill weave. I'll pass this around. See if I can find a plain weave. Here's the plane weave. The plane weave carbon fiber, so you see like 1 over, 1 under, 1 over, 1 under, so on and so forth. Repeating over and over and over. Okay, here's your plane weave. And finally a satin weave, which would have like multiple over than 1 under, multiple over than 1 under, multiple over than 1 under. So here is a satin weave example. This one looks a little bit like the twill weave, but it's actually going 3 over, 1 under, 3 over, 1 under, 3 over, 1 under, and so on and so forth. Okay? So you should be able, oh, this is actually just, this is a twill. I lied. Sorry, I'm a liar. This is your satin weave, which has been distorted slightly. Okay. It's got to get bunched up.
I have a quick question.
Yes, sir. Question.
So what would be like the mechanical property differences on the
what are the
different
mechanical
types of
property
weave?
differences of these various weaves? I'm glad you asked, and we'll talk about that later. Hang on to that question.
All right, no problem.
Okay, so here's an example of your satin weave. This is maybe a little bit better, but here you see 4 over, 1 under, 4 over, 1 under, 4 over, 1 under. Okay, so this here is a 4 harness satin weave is what it would be called. All right, so that's what you see kind of in the picture on the right-hand side. All right, so there are your various types of weaves. There are other, but these are probably the most common: the plane weave, the twill weave, and the satin weave. Right? Jenner asks, when would you use each one of these particular weaves? Well, the big difference between all three of these is their drapability. And that's kind of a fancy manufacturing word, which we'll talk about when we do get into the manufacturing of composites. But if you can imagine trying to create a composite with a lot of curved surfaces, you would generally want a fabric that is much more drapable than not drapable. Okay. And the more sort of these over under kind of weavings that you have in the architecture, the less drapable it will be. It's going to be harder for you to, let's say, get the plane weave around a sharp corner than it is for you to get a satin weave around a sharp corner, because there's sort of more of these over under stitchings or whatever inside of the plane weave. So hopefully that makes a little bit of sense and gives you an idea of the differences between the various weaves. All right. Now, I just want to touch in the last 5 minutes here of lecture on the third thing that makes up a composite, and that is the interface. All right. Remember, our composites are not composites unless we have all three. So the interface really is going to dictate how well load is shared between the matrix and the reinforcement phases. All right. Now, there is debate in the composite community about what constitutes an interface. What is the dimensionality? How far away from the surface of the fiber is the interface, et cetera, et cetera. People have literally devoted like PhD studies to, doing AFM tapping right near the surface of a fiber and seeing how far away from it you have changes in mechanical properties based on interface. It's just like craziness, all right? But the point is that there is this interface that exists between the fibers and the surrounding matrix, and it does have some thickness to it. Generally, it's on the order of 500 nanometers or less, all right? That's what I would generally consider. From the surface of the fiber outwards about 500 nanometers is probably a pretty good estimate as what you would call the interface or the interphase. All right. Now, when you have a fiber inside of a matrix, you can really have two types of bonding that might exist between that fiber and that matrix. The first would be what you're probably most familiar with is an adhesive bond. Okay, and an adhesive bond is basically just strictly a mechanical bond, right? Now, a cohesive bond or a chemical bond is the other type. And a cohesive bond is one that's much stronger, where you actually have chemical functionality at that particular bond. So let's talk about that with one more slide here, where we're just giving a little bit more detail on these two types of bonds. Bond, cohesive bond. Okay. No, adhesive versus cohesive. An adhesive bond, like I said, purely mechanical, and it's mostly this frictional bond. So one example might be if I had a piece of duct tape and I stuck it on the wall. That would be a mechanical bond. It's purely adhesive. There's no chemical reaction that's occurring between that duct tape and the wall. All right. There's nothing chemically that's happening there. Okay. That's different from a cohesive bond where you actually have chemical reactions between the two species that are being bonded. All right. So these cohesive bonds are really what we're after. And it's part of the reason that we apply the sizing to the surface of the fibers. Remember that sizing is that aqueous spray that we put on the fibers that gives like additional chemical functionality to the surface of the fiber. All right, so if you have a good sizing, that sizing will offer chemical cohesive compatibility with your surrounding matrix phase. And that's what we're kind of trying to show in the bottom right-hand image here, is that you have the silicon dioxide surface, which might be like the surface of a glass, and you have a reactive R group, which is part of the um, sizing that can then actually react with the polymer network, this cross-linking epoxy network, which might exist. All right, so it gives you this additional strength and bond that is really nice to have and really offers the best load sharing possible when you're talking about getting, let's say, your composite into compression, where we know that fibers generally without this load sharing would be absolutely terrible. Question? Yeah, the question is, can we have a cohesive bond without an adhesive bond? And probably not. I couldn't think of really a chemical reaction where you wouldn't also have some sort of adhesive going on there as well. I think that's kind of hard to achieve. Maybe. Um, I don't know. I can't think of one off the top of my head. Okay, so there you go. But these interfaces, and we'll get into this later in the class about failures of composites, these interfaces can be very susceptible to failure. So when you're thinking about analyzing these composite materials, yeah, you might want to think about, okay, what is the strength of the fiber? What is the strength of the matrix? But if you're not considering what is the strength of the bond between those two, you might have failure a lot earlier than you actually anticipate. So interfacial failure is a common failure mode for composites, and one we'll talk about later in the class, but you can have things like fiber pullout, where you're actually like pulling individual strands of the fibers out from the surrounding matrix to separate them. Then you got no load sharing, obviously, between the two. And you can have debonding between fibers in the matrix. You can have delamination between individual fabric layers, all sorts of crazy kinds of failures. So that's going to be it for lecture today. That's going to be the end of sort of the materials portion. We'll get into actually manufacturing of composites tomorrow. So thank you for coming.